Good morning, everybody. So today we have our third lecture and we're going to deal with electrical systems. In the last lecture, we defined models for mechanical systems. Today we're going to do exactly the same. We're going to apply the same modeling method to electrical systems. As a reminder, these lecture notes are posted in Brightspace before each lecture. So make sure you have the notes with you before our live lectures and use them to take notes. Same for the labs. Lab 1 and 2 are already posted. If you want to take a look at them before your lab session, that it will certainly help you. So today we have a rather simple lecture on modeling of electrical systems. You've taken some sort of electrical systems before, electronic courses before. So here we are going to not necessarily introduce anything new, except that we're going to try to connect this to the last lecture and see if the equations to derive for electrical systems can also be used to derive mechanical systems. And we will see that indeed they can. The mechanical and electrical systems will follow the exact same sort of differential equations. And you can then make an analogy between an electrical and a mechanical system. So by the end of this lecture, you should be able to model an electrical system, find the differential equations that describe the behavior of this system, and understand the analogy between mechanical and electrical systems. So let's get straight into it. Let's first define the basic elements that we need in our models. For a mechanical system, we define the mass, spring, and damper. Here we have the three elements are the resistance, the capacitance, and the inductance, or resistor, capacitor, and the inductor. So let's start with the very first one. A resistor resists against an electrical current. It provides resistance against the electrical current. And the higher the resistance, the more difficult it is to pass a current through that resistor. A resistor then here is represented by the symbol R. If we pass a current through it, this current will now create a voltage drop. And the voltage drop will be V2, the voltage on one end of that resistor, minus the voltage on the other end, V1. So as a function of the current, we know that that voltage drop, which in this case is V2 minus V1, is equal to, what is the voltage drop across the resistor?
Ri.
Ri. Exactly. So it actually is the opposite, is V1 minus V2. Minus V2 equals to R times I. Right? Very simple, nothing new here. What are the assumptions we made when you wrote this equation? Well, we are making a idealization, assuming that this resistance is a purely resistive load. There is no inductance, no capacitance. If you need to account for resistance, capacitance, or inductance, then you need the other elements. Now let's move on to the capacitor. The capacitor is an element that stores energy in the form of an electrical field. And again, once a current passes through this capacitor, a current I, a voltage drop occurs. The voltage drop that we can call here delta V, or again, V1 minus V2. And this voltage drop is as a function of the current. What is it? For a capacitance C, what is the voltage drop across a capacitor? I'll help you, 1 over C. What else? Integral of the current over time, dt. 1 over C, integral of I. Now this is the voltage drop across the capacitor as a function of the current. The assumption that we made here is that a capacitor has no inductance and no resistance. In reality, when you have a capacitor, there's always a little bit of resistance. If you need the resistance, then you need to connect the capacitor with a resistor that we just covered. The last element is the inductor. The capacitor stores energy in the form of an electrical field. The inductor does the same, but in the form of a magnetic field. A inductor, as the assumption you're making here, is that it has no capacitance and no resistance. So once a current I of T passes through this inductor, what is the voltage drop? Across the inductor. Any ideas? L times the derivative di of the current dt. L di dt. Okay, L di dt. Okay, very well. So these are the three elements that we need for our models. And now we can combine them in a circuit. So let's do one example right away. So here we have this LRC circuit, has a voltage source of V, three elements in series. And the question is, find the relation between the voltage V and the current and the charge in the circuit. So let's establish here a current in the system and a charge. Let's call the charge Q, the current I. Let's start now by modeling the relation between V, the voltage input, and I, the current. How can we do that? We can apply simply Kirchhoff's law here. And to do that, let's first define the signs here for the voltage drop. So that's the voltage source is the input, and everything else will have a voltage drop that goes in the opposite direction as that of the input, like that. On one end, higher voltage potential than the other one. What does Kirchhoff's law state? It states that the sum of all voltages in a closed loop is equal to zero. Sum of all voltages in a closed loop is equal to zero. How can you do that now? Now we can add everything. So let's go along the direction of the current. We see that when you pass through V, we go from negative to positive. So we can write negative V plus, now we're going through C by positive to negative. So that's along the current flow. So that's positive. So plus the voltage drop across the capacitor, which is
1 over C integral I dt.
Exactly, 1 over C integral of I of t. I'm going to omit here, dt, plus now the voltage drop across the resistor, which is Ri, and plus the voltage drop across the inductor, L di dt, and this is equal to 0. Of course, you can rearrange this and then just write Ri plus L di dt plus 1 over C integral of I dt equals to V. So here we have the equation that relates V and I. Very well. So now the next part of the question asks for the relation between the charge and the voltage input V. So to do that, we can use the equation we already derived and then replace I with its equivalent relation to the current. So then let me ask you this, what is the relation between the electrical current and the electrical charge?
Current is a measure of charge over time.
Exactly. Current is a measure of charge over time, which can be expressed mathematically as I equals to the derivative of the charge, dq dt. Right? The amount of electrons that have passed through a portion of the network at a given instant in time, or the flow rate of electrons. The derivative of the charge over time is the current. Okay, now we can take this expression and replace I with dq dt. So what do we get? We get R dq dt plus L d dt of dq dt plus 1 over C integral of dq dt equals to V. Okay, so now we can use our notation for make things easier. Remember the dot above and a variable that represents the derivative. So we get R Q dot plus L times
Q with 2 dots above it.
exactly Q double dot plus we have the integration here and the derivative will cancel out 1 over C times Q equals to V. And here we have the relation between the current and the input voltage. Okay, very simple, just Kirchhoff's law, nothing very complicated. Any questions here before we move on? No? A reminder that I don't check the chat. I have my monitor too far away from me, I can't see it. So if you have any questions, please use your mic.
So what was the reason for changing to charge instead of just leaving it as current? Is there
There is no specific reason, it's just that we want both equations. That's just the exercise, yeah.
Okay.
We can, both equations are valid. It really depends on what you're trying to model. Typically, the equation in blue is more useful when you do circuit analysis.
Cool.
Anything else? No? All right. So here is the equations we established. Now let's take this equation here and take a look at it. You guys remember from the last lecture, we derived an equation for a mass spring damper system, and that turned out to be a second order differential equation as well, where we had on one side of the equation the displacement or the speed and its own derivatives, and on the other side we have a input to that system, a forcing factor that I call in differential equations, and that was the force. Here we have a very similar structure. So there seems to be a these equations seem very similar. So let's see if they are indeed. Let's go back to what we did in the last lecture and consider again the mass spring damper system and compare that with what we just did. So here's the mass spring damper system. We have a displacement, that's our variable of interest here, and we have a input force. And for the circuit we just did, we have the same, and we are interested in the current, sorry, in the charge and the input voltage. So equation 1 is the equation we derived in the last lecture. F equals to mx double dot plus bx dot plus kx. The equation we just came up with is V equals to LQ double dot plus RQ dot plus 1 over C times Q. You see, these two equations are exactly the same. The only difference is that we are using different variables, but the structure of these equations are precisely the same. This suggests that the elements that we see in both of these systems are performing physically some things, a function that is very similar. And is that indeed the case? So let's see. Let's start with analyzing here maybe the relation between B and R. B represents a viscous friction coefficient in a mechanical system. And what is the function of that? Is to dissipate energy in the form of heat. That's what dissipates energy. The equivalent in our electrical system seems to be R, which is the resistor. And what is the function of a resistor? What does a resistor do in an electrical system? Precisely the same. It dissipates energy in the form of heat. And they then multiplied by displacement or charge. Let's see M. M is mass, that here represents the effect of inertia in the system, which tries to continue motion in a mechanical system. And in the electrical system, we have the inductance L. So what does a inductance do? It opposes changes in the current, opposes changes in the current, or opposes changes in the amount of charge in the system. And it's precisely the same function. We have an inertia in a mechanical system that opposes change in motion. We have the inductor that opposes change in the current in the electrical system. They perform precisely the same function. They keep the system going with some sort of inertia. Interesting, isn't it? And now let's look at the input factors here. We have F and V. F is the force, is the input to our system, is what creates motion. V is what pushes electrons through the system, is the equivalent of a force in a mechanical system. The higher V, the higher the charge in the system, the higher the current, the higher F, the higher the displacement, and the higher the speed in the system. The last element is not as intuitive, but we can see here, we have K, the spring coefficient, the stiffness coefficient, and 1 over C. So this is an indication of how compliant the system is to the establishment of an electrical current in an electrical circuit, or how difficult it is to create a displacement in the mechanical system. So the higher C, the easier would be, the harder would be for a charge to develop in the system, in the same way that the higher K, the harder it gets to displace, to create a motion in the system. So these two equations show precisely the same thing. The elements in this equation perform the same thing, we just call them differently, but physically, they are there performing something very similar. If we calculate the impulse response for the system, of course, depending on the parameters we use, we'll see that later, is not as straightforward as here, but one possible solution to that is equation 3, which is a sinusoidal and a exponential waveform that will describe both the current, the current and the charge, and the displacement and the speed in this circuit. Okay, so maybe you can actually go ahead and then create an analogy between these elements. This is a summary of what we just discussed. In a mechanical system, the input is the force. In the electrical system, the input is the voltage. A force pushes electrons through, creates displacement, whereas a voltage pushes electrons through the circuit. The variable of interest that we used before was the displacement, and the displacement was analogous to the charge. So if you now take the derivative of the displacement, that's the speed, and if you take the derivative of the charge, that's the current. So velocity or speed is equivalent to the current. Speed is equivalent to the current. You see, it's just the displacement, the derivative of displacement, the derivative of the charge, which are the variables of interest that we use to establish the equations earlier. The damping coefficient then becomes equivalent to the resistance. The mass is analogous to the inductance, the effects of inertia, or the effect of an inductor that creates a magnetic field to keep the flow rate of current going. Right? That's the function of an inductor. And the compliance of the system, or 1 over K, which is equivalent to the capacitance, or how easy it is to establish a current through the system. Okay, so for every mechanical system, there exists an equivalent electrical system that displays the same behavior. So if you are more comfortable with a mechanical system, if you don't want to solve an electrical system, we can create an equivalent circuit and then treat that with the same equations, and the other way around. Interesting, isn't it? It's exactly the same equations. They describe precisely the same thing. So with this sort of modeling, we can address both systems, and the analysis they're going to perform later on, they will apply to all of them. Are there any questions at this point?
Sorry, just what was the equation 3 in the last slide again?
This is the impulse response of the system. Apply, let's say, if we slap the mass, provide a high amount of energy to the mass and let it go, or we turn on and off the power source very fast. That the displacement or the charge in the system will follow that equation. We'll get into more details of that later.
Okay, thank you.
Yeah.
Professor, I have a question.
Yes.
So we know that there is an equivalent component for the mechanical system and electrical system. So which component is necessary, or which component can be removed, or we can just, it's an optional choice? Or is...
Well, that really depends on the system we are trying to model. It's a different question than making an analogy between one system and the other. If, for example, in an electrical system, the capacitance is too small, it may be neglected, an electrical or the inductance, but it depends on the system we are trying to model. And that's specific to the mechanical or the electrical system. It's not the analogy between them. How we account for them really depends on the system. The more accurate the model, the better. But sometimes we can make simplifications to get the process, to get an easier form of the equivalent model.
Okay, thank you.
Okay. Anybody else? Any other questions, folks? No? Yeah? Okay. All right, so we did mechanical, electrical. Let's see, later we can do an analogy with hydraulic systems, see if we can find equivalences there as well. Now let's take these two systems and analyze their responses. The question that somebody just asked me about, that sinusoidal waveform, that equation 3. This is the curve that you will get out of those equations. This is the step response or impulse response of the system. This particular one, you have step and impulse. So what does it mean? So let's take the mass spring damper system and the circuit and assign random values to it. Here I chose 5, 0.25, and 0.1 for M, K, and B, or J, 1 over C, and R. And let's apply a step and an impulse to the systems and see how they behave and see if this makes sense at all. Starting with the mass spring damper system. We are going to look at the output, which is the displacement, as a result of a step force. What does it mean to apply a step force to this mass spring damper system? We pull on the mass and we hold it. We pull on the mass and we hold it. And that's then a force that goes from 0 to a given constant value and remains constant over time. That characterizes a step input. What is that on the electrical system? Or how would you describe a step input to the electrical system? What does that mean to apply a step input to the electrical system?
Turning the voltage on.
Exactly, turning the voltage on and leaving the voltage, just leave it there on as time goes to infinity. So what happens? In the electrical system, the input is V and the output here is the charge that you're interested in. So let's see what happens. When we apply a force to the mass starts to move, it will oscillate. The energy goes from inertia to potential energy in between. Some energy is dissipated in the damper. That's why it oscillates and then eventually settles. It settles at a non-zero value. Right? Settles at a non-zero value, which makes sense. We are moving the mass and holding it, so the final value is non-zero. In the electrical circuit, what happens? The same thing. We turn it on. We are injecting charge into the system. It will oscillate. This oscillation is the energy converting between electrical and electrical field and magnetic field in the inductor and capacitor. The energy goes back and forth a little bit. In this process, the resistor is in the way that it dissipates a little bit of energy, and then eventually the charge settles at a constant value. Exactly same behavior observed in both electrical and mechanical. What about the impulse response? The impulse response would be equivalent to just slapping the mass, or just turning, or just taking the electrical circuit with a initial current in the inductor or a initial voltage in the capacitor and let it go from there. What happens to the voltage? What happens to the position? Well, if you slap the mass oscillates and eventually settles at 0. It will just oscillate around its original position. And because it's an impulse, it's just a short amount of energy, it's just an energy applied to the system in a short amount of time, and that energy is removed. The system oscillates and settles at 0. Same thing happens with the charge. When you turn the system on and off, or you just let it go from the initial condition, it oscillates and eventually settles to 0. So they both display precisely the same behavior. Now let's do the same analysis, but let's use current and the speed instead. We did charge and displacement. let's do current and speed because we know that these also are equivalent. And let's look at step and impulse response. Let's start with the electrical system, sorry, the mechanical system. Impulse again, in steps, let's start with step. We pull on the mass and you hold it. What happens to the speed? When you start to pull on the mass will start to move and eventually it will stop. And when it stops, the speed goes to 0. So that's what we see here. The mass starts to move and that's the speed. So once it settles at this position here, the speed becomes 0, it stops moving. What about the electrical current? When you turn the system on as in step, the current is established in the system and the current eventually dies off to 0. And why is that? Because we have a DC system and the capacitor here in DC is an open circuit and becomes an open circuit in DC and no current flows through a capacitor in a DC circuit. We can see that by establishing the voltage equation again, 1/C integral of I dt. And if we reverse this equation, we know that I equals to C times dV dt in the capacitor. And you see here, this is good. Let me put a capital V here to avoid confusion with the speed on the other side. So we have the derivative of the voltage, but the voltage is a step function. It goes from 0 to a certain value and it stays constant. The derivative of a constant is 0, and therefore current is also 0 once the system settles. This is to say that a voltage or a speed oscillates and settles at 0, so does the current. It oscillates and then settles at 0 because the capacitor becomes an open circuit in direct current. Let's look at the impulse response. It's the same thing we observed before. If you slap the mass, it oscillates and stops. The speed eventually settles to 0. Same happens to the current. If you let the system go from an initial condition, the current slowly dies off to 0. Two different systems, exactly same behavior. Okay. Any questions here? Yep.
Yeah. So I just want to ask, so for this electrical system, and only the DC voltage can be applied, if that's possible, and AC voltage can be applied?
A DC would be only direct current, so a constant input.
Okay.
And the AC is the alternating current, so something like a sinusoidal waveform.
Yeah, so in this case, only the DC can be applied.
No, we can apply both. We can apply a sinusoidal waveform to the input here. We can also apply a sinusoidal waveform as in the form of force in the mechanical system. And the result will be exactly the same for both.
Oh,
I'm limiting my examples to DC, to a step, because it's easier to understand. But if you go with a AC, that works as well.
Okay, so it could also realize the step response, but how? Because it's changed from time to time, or you just think about the in a certain kind of period, the result could be same.
If the input is something other than a step, like a sinusoidal waveform, then the output is also sinusoidal waveform that never settles.
Okay.
Never settles. Okay. It's the same as is a scaled version of the input.
Okay. Okay. Thank you.
Which turns out to be that it doesn't change shape in a linear time invariant system. Is the sinusoidal waveform. Yeah.
Sorry, the graphs on the previous slide are slightly different. Is that are these graphs for the mass and the spring system, and the ones on the next slide are for the circuit?
No, they are both. This graph here applies to both the mass and the circuit. Is the step response, and this is for position. This is for position. This graph is the impulse response of both the mass and the circuit. These ones here are for the speed, and this is the speed and current, and this is then position and charge,
Got it.
Okay.
Thank you.
Yeah. Any other questions here before we move on? No? Very well. So now let's try to expand this without equations, just thinking about what we saw, and let's try to link this to a hydraulic system. In our systems before, we had a electrical potential or electrical current. We had a voltage pushing electrons through the circuit. In a hydraulic system, we can assume that our variable of interest will be the flow rate. The flow in the system, which would be equivalent to the current. If that is the case, then what should be the input to the system? If we are now dealing with a hydraulic system, what creates flow is the pressure. So the pressure becomes equivalent to the voltage. The flow rate becomes equivalent to the current. What else? The quantity of fluid is the charge, or the integral of flow rate over time is the charge. And what else we have as equivalences here? The hydraulic resistance, which is, this one is easy to understand. Hydraulic resistance is the equivalent of the resistance in an electrical system. The hydraulic capacitance is what would store energy in the form of an electrical field in the electrical system. And this is here, the potential energy is stored in the form of liquid. So the hydraulic capacitance is our electric capacitance. If we have a tank, we are storing energy in the form of hydraulic system in the tank. And this energy is equivalent to the energy we stored in a capacitor in an electrical system. So let's summarize this. If we have two pressures here, pressure 1 and pressure 2, this pressure creates a flow rate. Right? The pressure drop is the voltage difference. So P2 minus P1 would be the equivalent to the voltage, the pressure drop, the same way that the difference in electric potential is the voltage. The difference in pressure is the voltage, the equivalent to the voltage here. That is what pushes fluid through the system. In the other example here, we have a flow coming in, Q1, subjected to a pressure 1 on the top of that tank, pressure 2 at the bottom of that tank. We have a output here that is a different flow rate, Q2, because you're storing energy in the form of potential energy. And here we have a way to store energy in a hydraulic system, which would be the equivalent of a capacitance in the electrical system. The only element that we haven't addressed is the inductor. So what is equivalent here to the inductor? Any ideas?
For example, I think if the liquid is in a cylinder and the force applied to the piston would be equivalent to an inductor?
The force applied to the piston would I think it would be more close to a pressure. Now you're inputting a pressure to the system. So let me ask the question differently. What was the purpose of the inductor in the system and the mass? They provided some sort of inertia to the system by keeping either the system moving or the current going, right? So what would be the equivalent here? What would keep the system just going once you remove with some sort of inertia? It's the fluid inertia itself. The equivalent of an inductor would be the fluid inertia, which in the systems that we are going to use to describe is fairly negligible and we can neglect it. Right? So let's recap. Hydraulic resistance is equivalent to an electric resistance. Hydraulic capacitance, or a tank or a reservoir or something like that, is equivalent of a capacitor. Fluid inertia, inductor. The input to the system is the pressure. The difference in pressure, or the pressure drop, is the voltage. And the variable of interest is the current or the flow rate in this particular example. If you take the integral of the flow rate, then it gives us the quantity of fluid. If you take the integral of the current, that gives us the charge. So the quantity of fluid is equivalent to the charge. So yeah, let's do an example here. We have, this system is a very simple system. It has a pump. It has a water reservoir here. And we have a hydraulic resistance R. We can call this P for the pressure applied to the system. We have the resistance and that. We can create now a flow rate. Let's call that flow rate Q. The equivalent of this in terms of an electrical system would be pressure becomes voltage, resistance, hydraulic resistance becomes the electric resistance. The storage here, the reservoir becomes now a capacitance where we are going to store energy in the form of a electrical field. Okay, and the flow rate is the current in the system, right? Same analogy that we did before. So we can, if you don't want to model a hydraulic system, create the equivalent electrical system, and we can model them that way. Okay. Let me give you a more concrete example of this. Let's consider this capillary plexus network. So this would be a network of veins, for example. And when we apply a pressure, blood pressure to that, the veins can expand and retain some amount of blood before they contract and let that blood keep going. So the example we can have here is a network of veins that is represented here. Now we have blood being pumped into the system through a heart artery that we see here. So this is the heart. So the heart provides an initial pressure. That pressure now pumps fluid into the network, and we see an initial flow going into the network. They're going to call that a QA. So this is the flow rate coming from the heart as a result of a injected pressure P of T. So this now goes to the network. The network now becomes some sort of storage element because it can retain some of the blood before it lets the blood out. So the flux in and the flux out are not necessarily the same because we are somehow storing it temporarily before we let it go. So now we have some sort of hydraulic capacitance here, some sort of reservoir that is holding for a few moments that quantity of blood. Because it's a physical system, we also have some resistance R. And once you overcome all that, then the system finally gets into a vein. And then we have a different flow rate. I call that a QV for vein, QA for artery. And we have also the resistance of the vein, RC. Right. So an equivalent model for this network can be shown here. The input is a pressure. We have an initial flow rate. We pass that through a system that has its own resistance and capacitance. It gets out with another resistance, and then there is another flow coming out. Here is a different way to see it. We have a hydraulic pump. We have a first resistance, hydraulic resistance. We have now a reservoir that stores that fluid, and eventually another resistance, and then the flow coming out of the system. So these are equivalent representations of the same thing. What would be now an equivalent electrical system that would represent the same behavior as we see here. I'll let you guys think about it. How would we create an equivalent electric system to represent the same behavior? So what do we see? Key points here are some way to store energy, some resistance to flow, the input pressure, and two different fluid flows, one before the reservoir and one after. What would be an equivalent electric system that it would have the ability to display the same thing?
You could just put a voltage source, a resistor, a capacitor, and then another resistor all in series. But you could simplify it and just put one resistor with the summed resistance.
Aha, very good. So you're almost there. So your idea is to put everything in series, right? Everything in series. The problem I see with putting everything in series would be that there's only one flow. The flow going in is the same as the flow going out, right? So that wouldn't necessarily represent this, because you see we have two different flows. We have the flow before we get into the network, and we have the flow after.
Could you just put the resistance for the capillaries in parallel then? Because it would branch off of the arteries.
We are getting there, very good. So let's start with the first part here. Let's start with the heart, the artery, and the capillary network first. We have the input. Well, with the input, it's easy. We have a pressure. So here that becomes a voltage. That will pass through a resistance. Let's call that RA. Before we get to the network, that has a capacitance, a way to store flow, C. And this is now we have here a flow, QA. So let's call that IA. That's the first part. And now from this reservoir, some of the fluid gets out. So we can now put another branch connected here. And this would be RC, and this is the second flow, IC. This would be the equivalent network to the pump system we saw. Where is the inertia? Well, we neglected the inertia, but if we were to add inertia, how would we do that? The fluid inertia.
Add a...
Yep. Add
an inductor.
Add an inductor. Well, one for each flow, and one for IA, one for IC.
Just follow the resistor.
Just before each resistor. Yeah. Okay. So this is again, because we know the function of each physical element in the system, we can go back and forth between hydraulic, electric, and mechanical systems. The equations that they describe are precisely the equations that are govern their systems. The systems are exactly the same. Now let's take this analysis one step ahead. And let's consider the left coronary artery model. An actual model would have about 14 segments. And here is one segment, one branch. Let's take this top branch here. We have blood being pumped in and then distributed through different branches like that. We can do an hydraulic system. We can do an electrical system. Here is the equivalent electric system for that particular branch. We have the input pump, the voltage, we have the resistance, we have the fluid inertia, and the capacitance if we consider that a branch can expand and contract, and in the process, it can store some blood. How are we going to expand this to do all branches? Well, this is one element, and now at this point here, it will split into three different branches. So we can now create a point here and go to three different branches. And along each of these three branches, we have again the R, L, and C to represent the respective inductance, the respective inertia, resistance, and hydraulic capacitance in that specific branch, and so on until we get to the end of this network. And at the end of this network, we have other veins and other things going into the body. We can model them as simply an impedance attached to the end. So if you expand this simple network from one branch to all 14 branches, we should have something like that. And you see, here is the heart, here is the pump, V. Here is the first node that we had, and then this node just keeps opening up and splitting into other branches. And at the end of these branches, the blood needs to go somewhere to the cells or something like that. We can model that as a simple impedance attached to the end of these branches. So these impedances would be at the tip here. Once we reach the end, we add a impedance to account for that. Okay. So this becomes simply an electric circuit. And now we can solve for this. If you want to find the fluid flow here, we just look at the equivalent circuit and calculate the current out of that specific point there. If you want to know how much pressure this is going through these points, just look at the voltage drop across those 2 points in the network, and so on. Here is a simplified model for that. Now we basically have an electric circuit. And now if you want to solve for these variables, we can simply use whatever model or whatever method we want to solve for the variables of interest. One method here is the admittance analysis. I have the equations here. I can put more information later. We're going to use something else, but this is one way to now solve for the circuit. There are many different ways. This is, for this particular network, is relatively easy to use. But there we can apply Kirchhoff's law as we did before and just take a branch there, create a loop, and solve for the variables of interest. You're going to do some examples about that later. I will add the equations that we would result from these just for information, but you guys don't need to focus on this analysis. This is a bit beyond what we need for the course. I just wanted to show you that now what we are modeling here seems to be a biomedical, it is a biomedical system, seems to be a hydraulic system, and yet the analysis we are conducting to solve for it becomes a lot easier if we go with a equivalent electrical system. Okay, interesting, isn't it? Are there any questions before we do some exercises?
So we don't need to take notes on this model. This won't appear in anything, right?
Not this this admittance analysis. No, we're going to use something else. So for this later. So this is just for more for information as one possible way. Right? What I want you to retain from this is how we went from a hydraulic system to the equivalent electric system, and then later we just need to solve for that electric system. The process of creating these analog systems is what I want you to retain from today's lecture.
Are there equivalent, like, are there transistors within the body?
A transistor, no, maybe, but a transistor is a nonlinear system. Might be a nonlinear system. It's more like an amplifier. So I don't think we would be encountering.
Okay.
Transistor, yeah, it is. Transistor is, depending on how you use it, it could become a nonlinear system, so we cannot account for it.
I just want to ask if we need to know how to simplify the model, like from the previous slide to this one.
No. I just wanted to this is not this is just a few branches from here to there. Okay. Otherwise, it would become too complicated. You don't need to worry about that now.
Okay, thank you.
All right. So any other questions before we do some exercises? Okay, so let's do exercise 1. We have this circuit. This circuit, when you look at it, it's an electric circuit, but it could very well be representing a hydraulic system or a mechanical system. For this system, we want to write the differential equations that relate to the voltage and the current in each of these loops. So to do that, we apply Kirchhoff's law and we find the equations for both I1 and I2. Okay. All right, so let me get started with that. So first things first, here is the circuit we want. We want the relation between this voltage and the currents in each of these loops. So let's define the current in these loops. Let's call this current here I1. And let's call the current flowing through the entire loop here I2. And let's perhaps start with this loop. So sum of all voltages equals to 0 in this loop. Sum of all voltages equals to 0 in that loop. Because this is the input voltage V, we know that a sum of voltage across R and L will be equal to V. Right? Remember that we did the plus, minus, and this one is negative. When we move it to the other side of the equation, it becomes positive. So sum of voltages across R and L equals to V. So let's do that. So V equals to voltage drop across R, which is what is the current flowing through R? Is simply I1. Yeah, I1 times R plus voltage drop across L, which is L times di dt. So now we have a little bit of a difference here because we have current I1 going downwards and you have current I2 going upwards. We are following the flow of current I1. So current I2 is going against it. Now we have to account for the difference in these two. So that would be dt of I1 minus I2. And why minus I1 minus I2 and not the other way around? Because we're following I1. So this is the positive current flowing in this direction is our positive reference, right? And that current is going against it, it becomes negative. Okay, so I1R, L, D, the derivative of I1 minus I2, or the net current through L. Okay, is this clear? Is this clear? Yeah. Can you move on to the second loop? Yep. All right, so let's do the second loop. Let's do the second loop here. Let's start with now, well, if we do the sum of all voltages here, that equates to 0 because we have no input voltage like we had there. So sum of voltage across R plus voltage across C plus voltage across L is going to be equal to 0. So let's start with R. We have R times the current through it, which in this case is I2, plus voltage across the capacitor, 1 over C integral of I2 dt, and plus the voltage across L. Now we are following the direction of I2. This is our positive reference now, is the direction of I2. So tell me what the voltage drop is there.
It's I2 minus I1.
Exactly, I2 minus I1. Very good, and this is equal to 0. Okay. Any questions? Any questions? No? All good? Now, if we would...
So in the second loop, why isn't there a voltage? Like the voltage from the first loop just doesn't affect the second loop at all?
Directly, no. We have, because you're looking at this loop, right? This is where the input is. On this loop here, the voltage is not included.
Right.
If we did maybe this loop all the way like that, but we have to redefine the currents, then it would show up.
Okay.
Of course, V is influencing I2, right? That's what pushes I2 there as well. So there is an indirect cause there.
Right. Yeah.
Any other questions? No? Okay. There are no questions. We can move on to something else. So now what we could, also a question I could ask here is, what if we want the relation between V and I2 directly? So you see, you have two different differential equations here. They both depend on I1. We could isolate I1 here and replace there. This will become a very complicated differential equation to solve for. So to solve for this, we need to make this process a lot easier. And that's what we're going to see in the next lecture. So take the Laplace transform of these two equations, and so we can replace I1 from this equation there and then solve for it. So using Laplace, this will be a lot easier. Okay, any other questions here? No? Okay. So if there are no questions, I will let you guys take a look at exercise 2, as and then I'm going to erase what I made here. I think based on what we just did, you should be able to solve it fairly easily.
Just like you said with the last, you said that the Laplace transform basically, like it's like a change of variables, basically. It like enables you to analyze I2 in terms of V through I1.
Yes, exactly. And this is exactly the word I was looking for, is the change of variables. We are now replacing derivatives with the Laplace operator S. Integrals will also be functions of the Laplace operator S. So all derivatives and integrals will be replaced with some sort of S, the Laplace variable, which makes our job a lot easier. And then once we find the equation between I2 and V, we just take the inverse Laplace, and then we have the response. We're going to see that in the next lecture.
Cool.
Okay. You guys, you took differential equations, right? Before. Yeah, so what you're going to see in the next lecture is not what a Laplace transform, how we apply Laplace transform, that we know. What I want us to focus on in the next lecture is what exactly a Laplace transform represents. Beyond just doing the math, what exactly does it do? What is it trying to capture? And that's what I'm going to focus on. And then, of course, do some exercises where you can apply it mathematically. But there is a very important message behind Laplace transform that we need to understand. Beyond just looking at a table, doing inverse and forward Laplace.
Cool.
Okay, exercise 2. Now let's find the differential equations between I1, I2, and V in this example here. So 2, there we go. So let's get started with this one. We have I1 following in this branch, and you have I2 following in that branch. Let's start with this one. Now you guys know how to do it. I will just tell me what to do. V is equal to, for the first branch here, V is equal to
L times di1 over dt.
L times di1 dt. Very good. This is supposed to be L. There we go. What else? Plus
R,
which is
2
2. Actually, let me put it in just right, so we know what we are talking about. So this is R.
times
Let's call this R1. Times
I1 minus I2.
Times I1 minus I2. Right, which is V equals to L. L is supposed to be 2. So 2 di1 dt plus 2 I1 minus I2. And that's all. All right. Second loop, what do we get? Second loop right there. Let's start maybe with this R here. Let me call that one, just to avoid confusion. Call this R2.
R2 times R2.
R2 times
Plus L.
that L, right? That L times
di2 over dt.
dt. Very good, very good.
Plus R1. I2 minus I1.
Excellent. Minus -1. There. Right, and now we can replace these are two. Just number 2. There, so 2I1, 2I2 plus 2di2 dt plus 2I1 I2 minus I1 equals to 0. And of course, we can further expand here. We have 2I1 plus 2I2 plus 2I2. So that's 4I2.
Is there a positive sign in front of R1 bracket I2 minus I1? Or is there a negative sign?
It's all positive here.
Okay.
Right here. Are you referring to this point here?
Yeah.
Yeah, that's positive. Yeah.
Because of the loop orientation, wouldn't it be negative in the second loop? Or does it change?
Let's see. So let's see. So let's put it here. If the current is flowing this way, the potential here is positive. Potential there is negative. Potential here is positive. Potential there is negative. Current I2 goes up. Potential here is positive. Potential there is negative. So we always enter the element from the positive, get out from the negative. So it's all positive.
Right. So and that will be defined differently in the first loop then?
The first loop will be this a small difference is that here the voltage is the external voltage applied to the system. So this is positive, this is negative, positive, negative, positive, negative. If you follow I1, right? So you see that from this one here and that one, we go from positive to negative, positive, positive. When you pass through the input voltage, you go from the negative end towards the positive end, so minus V, which moves to the side of the equation as plus.
Cool.
Professor, so is that how it always is in every circuit that has like an external voltage?
Yes.
Yeah. So that you always enter the voltage from the negative end?
Right. Correct.
Thank you.
Okay. For this is only valid when there's one, right? If there's more than one voltage, then you need to know to analyze the system further and in which way it is applied. Okay. All right, so let's do one more exercise. Any other questions here? No?
Sorry, how do you know if it's internal or external voltage? Like, how do you know what signs to put to begin?
If this is V, it must be an external voltage because there is no element in a circuit that it just creates a voltage. Here we are dealing with voltage drops because of a current. This element must be the input to the system. If it is just V and is not coming from an element, then it is certainly external to the system.
Okay, so you just assume to write like the plus on the top of the V symbol. Like I just don't know which way to start.
When the voltage is applied externally to the system, it is always making the current flow through it like that. So the current will always enter the negative sign and the positive side like that. As the current goes through this element, this is different because this is the input to the system, just like an external pressure applied to it. This one is like a pressure drop. On this side, it has more pressure than on that side because some energy is lost in the process of passing through that.
Okay, thank you. That explains it.
Okay. Right, so let's do one more. So here's an even simpler circuit. I should have come up with more complicated questions. Here's exercise 3. Differential equations between the input voltage V and the output voltage V out, which in this particular case is defined as shown there. So how many equations do we need to now link V out and V in, the input to the system? What is the procedure? We cannot link V out and V in directly. We have to pass through the current in the circuit. So the first equation you can write is an equation between V and the current. And once we have established that, we can create a second equation that relates V out and the current. So I'll let you get started with the first one, just relate V and the current through the circuit. And then once I'm done erasing here, we'll solve it together. Okay, so here we have the circuit. It's a very simple circuit, just one loop. But now we want the relation between V and V out. We cannot directly connect them. Well, we could say that a V plus R plus V out equals to 0, but that doesn't really help us much. We can do a loop here with a current, relate V and that current, then relate the current and the output. If you want to simulate the system, that is probably a better way to do it. So let's establish a current here. Let's call that current I. So voltage is applied to the system like that. So this becomes positive, negative, positive, negative, positive, negative. So tell me what the equation between V and I is. Just start with that.
V equals Ri.
Ri, very good.
Plus 1 over C. Integral of I dt. Plus Ri.
Plus Ri. Very good. So V equals to 2 Ri plus 1 over C integral of I dt.
Professor, just one simple question. So for this case, can we consider their relationship as the voltage divider?
You could, yeah, you could do a voltage divider for sure. Yeah. The only issue is the capacitance here. So your voltage divider will end up with an integral.
Okay, I see. Thank you.
Yes, but then if you do a voltage divider, you just need to use V out and this voltage here, right? The voltage drop here and there.
Yeah,
and
exactly.
Yeah. So it solves part of the problem. Well, let's do a more comprehensive way where we have access to the current as well. This is one equation, and what is V out? What is the equation now between V out and I?
Ri plus 1 over C integral of I dt.
There you go. It's just the voltage drop here plus the voltage drop there. So V out is Ri plus 1 over C integral of I dt. Voltage drop here plus voltage drop there. Output voltage of the system. Okay, so here we have the two equations, equation 1, equation 2. And if you now want V out towards V, we can replace I there. Eventually, that becomes a voltage divider. The problem with our analysis here is that this is a differential equation now. This is I, this is the integral of I. How do we solve for that? Well, we can apply the Laplace transform to this. We'll see this in the next lecture to remember what the Laplace transform of this equation would be. So what is the Laplace transform of the integral, for example? Do you remember that from differential equations? V out becomes of t becomes V out of s. I of t becomes I of s. And integral of 1 of I of t becomes 1 over s times I of s. We'll see this in the next lecture. This gives you an idea of why we want to do that. It's because now you see the integral disappeared. We have s here. The integral here will also disappear, be replaced with 1 over s, and now it makes it a lot easier to replace one equation into the other and solve for the inverse Laplace, or even finding, you see here I and I, we can isolate them, solve for them even, because the integral basically disappeared. Right? So that will be the focus of the next lecture.
Professor, can you define S for us again? In this case, it's just a Laplace variable.
Yes, S is the Laplace variable, which is sigma plus omega j.
Cool.
From the next lecture, we'll deal with that in detail. And then from there on, once we are able to convert these equations in the Laplace domain, we are going to deal with them only in the Laplace domain. It makes the manipulation a lot easier. Any questions here?
So back to the question we just solved. For the V out, did we apply Kirchhoff's law? Because it looks like we did, but it isn't a closed loop, right?
For the second one here?
Yeah.
For V out? Yeah, no, this is not Kirchhoff's law. If we were looking at the voltage drop, for example, if we had defined V out over C, for example, right? V out would simply be 1 over C integral of I dt, right? But we define V out as the voltage drop across C plus the voltage drop across R. Right? It's this entire voltage drop here. So that plus that. That's why we have the summation over here. And again, if the voltage drop was only defined across C, it would just be this part of the equation. If the voltage drop was only defined across R, this would be the solution only. But it's because it's both and they are in series like that, then we can simply add them up.
Okay, thank you.
Okay, we have time for one more. Let's do this one. And you see now, you're probably tired of this easy exercises. Let's do one more there. And then we're going to stop here. And if you guys have any further questions after the lecture, just a reminder that I will be available for office hours for 1 hour in another Zoom link that is posted. And I'm also available on Tuesdays for 2 hours after the lecture if you have any questions. And another reminder is that labs 1 and 2 manuals are posted, and you can start working on them if you like. That will give you some advantage when you get to the actual labs. Although it's not required, you would have a much easier time in the lab during the lab if you take a look at it earlier. And given that the labs are 25% of the grade, that might be worth it. Okay, very last example, an easy one again. Here we are. Let's model this. Let's just start with loop 1, current 1. Current 1 going in a loop, of course, like that. So V equals to
I1 R.
I1 times R. Yeah, I1 times R.
Plus R times the I1 minus I2.
I1 minus I2. Very good. Why not I2 minus I1? Because we are following this current, and that's the positive reference for us. I2 goes up, it goes against our reference, hence the negative sign. So if we further expand this, we have 2 RI1 minus RI2. So this is one of the equations. Second one here. Let's just start with this top capacitor, resistor there. We have R times I2 plus voltage drop across L, which is L times di2 dt, and plus the voltage drop across here. Now, this is our reference. So going up here is positive, going down is negative. So plus R times I2 minus I1 this time. And this is equal to 0. Okay, so now we have here, if we expand this, we have 2 RI2 plus L di2 dt minus RI1 equals to 0. This is the second equation. And finally, here we have this VL as the output of the system. What is VL? What is VL?
Just L di2 over dt.
Yeah, L di2 over dt. Excellent. I should have come up with something a bit harder. There we are. But this is enough for the purpose of this course. Okay. So remember, let me ask this question again. If you take the Laplace transform of this equation here, what does that give? If you take the Laplace transform, V of t becomes VL of S equals to L times the derivative becomes in Laplace. Do you guys remember? Derivative becomes S and times I2 of S. Right, so the derivative disappears, is replaced with S, and that makes our process a lot easier to manipulate these equations. This is the subject of our next lecture. Okay, very good. We have a few minutes left. Any questions?
I just want to ask, so for this kind of question, we can solve the problem, just use the KVL or KCL. Because,
to establish these equations, yes, this is enough.
Okay, but I think for this case, the KCL probably easier because the KVL, well, I think it's some kind of more complicated. And the other question is that, will you give us some like the actual practice? Because I think this one, I mean, I'm not sure if it is enough. This kind of question in the lecture is enough for the easy exam or the quiz.
I'm not giving practice exams. That's not how.
Oh no! I mean the practice problems.
Right. So will come in the assignments. Some practice problems. These are already have 4 here, and we are going to come back to this because this is the first step in our analysis. It's just to establish the equations. But this is not enough. We want to solve for all this. We want to see what the response is when you apply a step to V, when you apply a sinusoidal waveform to V, when you apply an impulse. So this is for step one. Step one is this is enough. Now the next step is let's solve these equations. Let's attribute some specific inputs and see how the system behaves so that later we can control them if we know the input-output relationship.
So when will the assignment will come?
The first assignment will be by mid of next week.
Okay, thank you.
Okay.
So usually we will have like the 1 week to solve it, or?
At least 1 week. Yeah.
Okay, thank you.
The deadlines will be posted on Brightspace. Okay, folks, there are no further questions. I'll see you again on Tuesday. Yeah. Have a good weekend. Don't forget to go vote on Monday. And I'll see you again next week. If you have questions, I'll be available during office hours for 1 hour for now. Okay?
Thank you.
Have a good day.
Thank you.
All right.